So I have just the illustration from the previous couple of videos where we have an attempt to have representation of the signal, that is of a kind of random staircase signal. You see here it is having the amplitude 3 for the interval 0 to 1 here up to this particular point, and then onwards the amplitude level has got changed to 4 for the span 1 to 2 at this particular point. Next to that the amplitude level has dropped down to the level 2, then it has to the level 5, next to that to the 4, then for the two successive intervals we have the amplitude level 3, and thereupon we have 4. So this much of signal we have discussed in our previous video, whereupon the functional bases, which are the translated versions of the wavelet scaling function, Haar scaling function. This is the original Haar scaling function representation by phi of t, which is having amplitude level 1 for the time interval 0 to 1 here. By translating it onto the time axis, here it is the time axis, you can denote it by small t as well. We have the translated versions. By 1 unit, if you make translation on the right hand side, it will be phi of t minus 1. Translation by 2 units, it will be phi of t minus 2. Translation by 3 units, phi of t minus 3. So this way we have phi of t minus 4, phi of t minus 5, phi of t minus 6, phi of t minus 7. So when we use these functional bases to be the set here, we have called it to be the functional space defined as capital V0 here. So for every such a functional base here, which is a translated version of the original Haar scaling function, we have to make further scaling to achieve the particular amplitude level. So for this one, it should be scaling by phi u. So we can have the representation of this amplitude level as phi u times phi of t minus 3. So for this amplitude level, we can have the representation 3 times, as this is the amplitude 3, here it was the earlier phi u, 3 times phi of t minus phi u. So this way, if we have the representation and if we are successful to correctly convey the information as we have graphically illustrated here, we can call that this is the representation into the functional space capital V0 here. Next to that, we had seen one more illustration where it was another random kind of the signal where the amplitude levels into the unit intervals were not constant, they were either linearly varying or randomly varying. That created the need to have more finer versions of these functional bases here. That is why in general we have Vj as the functional space. The next functional space after V0 was obtained by reducing the time interval for the base functions by half here. So it was made to the half, so reduction factor was 2 here. So that time we had obtained the V1 as the functional space, and this was the mathematical expression to denote the same here, where the functional basis, you see phi of 2t, phi of 2t minus 1, where the 2 to be constituted for phi of t only. So this phi of t, which spanned for 0 to 1, is represented by the 2 here. So this is 0 to 1, we have make it half, 0 to 0.5 and 0.5 to 1 here. So this is the another functional space we can call. So after V0 we have V1 here. So let us have the representation of the signal that we have shown with the help of the solid line starting at the amplitude level 3 and ending at the amplitude level 4 here by using the functional space V0, that is making the use of base functions from this set, and then from V0, which is making the use of the base functions from this set here. So on the next slide you see the signal denoted by f of t here. So f of t we represent by the use of V0 as the functional space. F of t is equal to 3 times phi of t added by 4 times phi of t minus 1 further added by 2 times phi of t minus 2, added by 5 times t minus 3, phi of t minus 3, further added by 4 times phi of t minus 4. Next to that we add it with 3 times phi of t minus 5 plus 3 times phi of t minus 6, and at last the addition is with 4 times phi of t minus 7. So this is the functional representation by V0 functional space. If we make the use of functional space V1, we get this representation. See, this is the generalized representation for the signal that we illustrated earlier. So you see these two terms, 3 times phi of 2t added by 3 times phi of 2t minus 1. So we have the two translated versions after reducing the time interval of the original scaling function by factor 2 here, and both are having the scaling by the same factor, as for that particular span we need the amplitude level equal to 3 here. So for every term in the earlier representation we have two terms in the new representation. So for 4 times phi of t minus 1, we have 4 times phi of 2t minus 2 added by 4 times phi of 2t minus 3. 2 times phi of t minus 2 will be constituting the two terms, as like here you see the same scaling factor 2 multiplied to first of all phi of 2t minus 4 and then phi of 2t minus 5 here. So these two representations are conveying the same information, but by the use of different functional spaces that we have defined as capital V0 and then capital V1 here. So now to see the two terms for every term of the earlier representation, in general we can say that capital V0 functional space is contained into the capital V1 functional space, or in another words we can say V0 is a subset of V1. You see, capital V1, the functional space, is more finer functional space than that of the V0, and it can contain all the signals into the V0 here. Here we have V1 to be the bigger space than that of the V0 here. Why is it possible? Because the basis of V0 itself can be represented using the basis of V2. We have just now seen that for every functional base, as it was 3 times phi of t, we have substituted it by 3 times phi of 2t plus 3 times phi of 2t minus 1. We have substituted 4 times phi of t minus 1 by 4 times phi of 2t minus 2 added by 4 times phi of 2t minus 3, and so on here. So now here, for example, let us have phi of t is equal to, as represented here, and phi of t minus 1 here. So on the left hand side we have the functional basis from V0, and from the right hand side we have the functional basis from the capital V1 here. See the relationship between the functional basis from the two functional spaces V0 and V1, we can call the last two formulas to be the scaling relations, or most popularly it is also known by the term refinement relation, or you can also call it to be the dilation equation here. So as just now we have concluded that V0 is a subset of V1, similarly we can also prove that V1 is a subset of V2. So that is, any signal into the V1 can be represented using the basis of V2, and again this is possible because any basis of V1 can be represented using the basis of V2. We shall show you phi of 2t can be represented as phi of 4t added by phi of 4t minus 1 here. So for phi of 4t you will have the time interval 0 to 0.25. Here you will have 0.25 to 0.5 here. So originally phi of 2t is spanning for 0 to 0.5 only, half of the interval as compared to the original Haar scaling function here. So this way we can have the reductions to obtain more and more finer versions of the Haar scaling functions here. And we have also seen the relationship as we go on to obtain more and more final resolutions into these scaling function versions of the Haar wavelet here. So in general, the relationship between them we can represent like this. So you start at V0. So you can see V0 is a subset of V1, V1 is subset of V2, and in this way you can go up to V infinity. This is the theoretical writing here, but practically we will have a certain real number in place of infinity where we will be stopping here. In the left hand side we can have V minus 1 to be the subset of V0. So for V0 the scaling function was spanning for 0 to 1 with the constant amplitude level equal to 1. In the V minus 1, of course the constant amplitude level will be equal to 1, what we can scale to any value by just multiplying it, but it will be spanning for, let us say for example in this particular case 0 to 2 and then onwards 2 to 4. So this way we can have more combinations here. So what the relation is important here, what you can also outline here can also be illustrated with the help of the diagram here, which is more prominently obtained and known as the nested spaces diagram here. So I will show you the nested spaces diagram. Here you see V0 is the inner circle where this V0 is a part of V1 also, and this V1 is also a part of V2 here you see, and this way we can go for any positive numbers or the negative numbers inside this V0, what we can call the nested spaces. So for the nested spaces, the very important thing to note down the refinement relation, the relationship between the different functional spaces we have obtained while achieving the final resolutions or the coarse resolution of the functional spaces. So this was the topic, nested spaces. Here we can have the relation between the functional spaces defined for, let us say in general, R square or R cube. So if you compare it to the vector spaces in vector algebra, as we define the two-dimensional functional space by only two axes, let us say for example x and y, and if we add it one more axis, so we can see it to be the three-dimensional space here. So in general we can say that the two-dimensional functional space in vector algebra is the subset of three-dimensional functional space. What it was missing into the two-dimensional functional space? The third coordinate axis. So if we have only two axes x and y, it is two-dimensional functional space or the vector space you can say. And if we add z axis, which is again mutually perpendicular to the earlier x and y, so we can say that it is mutually perpendicular, means the condition of orthogonality is satisfied. Further also we can prove the condition of orthonormality proved here. So by adding one more functional base to be the new axis here, we get it to a new functional space here, and we have such the Haar wavelet function where it is possible to have decomposition of the signal components, and with the help of various types of the weights here we can achieve the signal processing applications with good efficiency here.